staan? We kunnen wel plaatsen.
Herewith I open this academic ceremony in which Mr. Van Wagenberg will defend his academic thesis, Advantage in Dose Calculation and Treatment Verification for High-Dose Rate Brachytherapy. I welcome you together with your paronyms and I wish you lots of success. I welcome, of course, also your supervisors, Professor Verhagen and Professor Fonseca, and of course the members of the opposition, whom you will meet later, and of course all your family, colleagues and friends on site and online. But before we start the opposition, I give you the floor to tell your family and friends what your thesis is all about.
Yes. Thank you, Pro-Rector. Dear Pro-Rector, members of the opposition, colleagues, friends and family, in the next 15 minutes I will present an overview of the research that I performed during the last few years and also show its main outcomes. I don't think that cancer needs a very comprehensive introduction. However, I want to show you some numbers. In the year 2020, when I started this research, around 10 million people died of cancer, which is 1 in 6 people that died that year. And 19.3 million people were diagnosed with cancer for the first time. That's of course a lot of people, but luckily we have a lot of ways to treat cancer nowadays. These methods include surgery, chemotherapy, immunotherapy, and of course radiotherapy. And on that last one, I want to zoom in a little bit. The principle behind radiotherapy is that high energy radiation can damage DNA strands and kill cancer cells. Of course, as you can imagine, this high radiation can also damage healthy cells. And therefore, in radiotherapy, it is a challenge to try to give a lot of dose to the tumor, but at the same time, keep the dose to the healthy tissue limited. A way to deliver this dose is using external beam radiotherapy that you can deliver using a linear accelerator. Here you can see an image of a LINAC or linear accelerator. The patient will lie down on this couch and you have this device that shoots a beam. That beam can be any shape and can rotate around the patient. Another way to deliver radiotherapy is using brachytherapy. Brachytherapy uses a very small radioactive source, the size of a grain of rice, and that source is usually located within a device called an afterloader. This device is shielded, so you can normally just stand next to it without getting any radiation. However, when we want to treat a patient, for example, a prostate patient, here you can see the prostate, so that's the blue area here. And then we are going to implant some needles or catheters that will reach all the way up to the prostate in this case. Once we verify that they reach the right spot, we can connect them to the afterloader using transfer tubes. And then everybody else except for the patient has to leave the room. We can start the treatment and the source will travel through the transfer tube and the catheter or needle to the prostate. Then after the treatment, the source will go back again and the treatment is finished. So what are the differences between these two modalities? Because you have the source on the inside, you can give a very high localized dose to a specific spot, compared to external beam radiotherapy, where you always have a beam that has to go through some other tissue before you reach your tumor. Also, for brachytherapy, in general, less fractions are needed. You can give more dose in one fraction, meaning the patient only has to come maybe 3, 4, or 5 times, while for external beam radiotherapy, this can be 15, 20, or maybe 25 times. This also makes brachytherapy a bit more cost-effective. However, of course, it's invasive because we have to place needles. And the last thing, for brachytherapy, there have been less technological tools and developments over the last years. So in this thesis, we worked on it because we think that using new innovations for brachytherapy, we could make it an even better treatment method. We looked at 2 different areas where we wanted to innovate. So these areas are dose calculation, which was described in chapter 2, and also treatment verification, which is described in chapters 3 to 6. To give you an understanding of what these things are, I want to give a more overview of the actual treatment of a brachy patient. So the first step is always, after the needles are inserted, of course, to do some imaging. This can be a CT image, an MRI image, or an ultrasound image. In this image, we have to define specific structures. You want to know exactly where the tumor is, where the organs are, but also where the needles are, because you can only put your dwell positions, your source positions within those needles. The next step is to optimize your plan, and that's where dose calculation comes into play. You want to, you're going to use an algorithm that's going to define the best spots for the source to stop so that you get a high dose to your tumor, but a low dose to your surrounding organs. And this you usually do with a dose calculation algorithm. So that's what chapter 2 goes into. So typically you can put your dose algorithms that you can use on a scale. On the left side, you have very fast dose calculation algorithms that are generally a bit less accurate. And on the right side, you have slower dose calculation algorithms that can be very accurate. Those we can use in research to exactly calculate how much dose we give to the patient. However, in the clinic, the focus is more on the faster dose calculation algorithms. And even though they are a bit less accurate, they are favored because, as you can imagine from the previous slide, the needles are inserted already during the imaging, and those needles have to stay inside the patient during this entire process. So you want to do it as fast as possible. There are some new developments where we try to create algorithms that are a bit more fast and also more accurate than the current clinical practice to create better plans. In chapter 2, we evaluated such a commercial new algorithm for liver cases, which are at the moment not really treated with brachytherapy. So this figure is quite complicated, but I will try to explain it a little bit. So the lines here represent the dose that you give. And for example, in this case, we see there is a colon. That's an organ with a lot of gas. And that means that there are some uncertainties there. The yellow line is the algorithm that we evaluated. And you can see that it's close to the dark blue line, which is the algorithm that is the most accurate. And a little bit further out, you can see the light blue, which is an algorithm that is currently used in the clinic. Then the next part of the thesis mainly focuses on treatment verification. So once you create this plan, the next problem or the next step is to actually treat the patient, like I showed previously. However, currently there is no way to accurately verify if the source went to the exact positions that you planned it would be. And this can have implications for the patient because we don't know if we, on accident, don't give the dose that we planned to give. And we could only find out about that, for example, sometime, maybe weeks later, if the patient doesn't react to the treatment. That's why we worked on the development of IRIS, which is short for the Iridium Imaging System. And the principle is basically that here you can see some needles in where the radioactive source, that is the green ball, travels through. At the same time, we have an imaging detector, imaging panel close to the patient that constantly acquires data from radiation coming from the source inside the patient. And we analyze that data and use it to track the source. So in the next few slides, I will show you the way from concept to clinical prototype, which was also described in chapters 3 to 6 of the thesis. So we start with the concept, and the first test we usually do is in a water tank, because as physicists we think that is close to a real patient. But actually there the method worked quite well. But when we moved to a more realistic shape, so this is a 3D printed phantom that has the shape of a real patient taken from a CT, we saw that because of the uneven surface that we have here, that previous approach didn't work well anymore. Then we switched to a new approach where we use high-density markers that are just above the surface of the panel, and the projections of those markers we can detect on the panel, and we can use that to triangulate the source position. That worked quite well, and then we moved on to even more complex phantoms. So here you can see a head phantom that is printed with different materials. So here you can see there is some high-density bone mimicking material in there. And in this phantom, we also tested if we could detect some treatment errors that can occur during a treatment. For example, if by accident 2 of the tubes are not connected to the right needle, or if the afterloader doesn't push the source to the right place. Then the missing link is that our phantoms are all static, and of course a patient can move. We tried to do some simulations using that by developing a motion platform, and we put our phantom on top of the motion platform and move it during our measurements. We saw that we could distinguish between the motions that we simulated and the source motion, because the source in general moves much faster than we expect a patient to move. In the end, this led to the development of a clinical prototype of IRIS. So here you can see the prototype. The imaging panel itself is a bit hidden behind blue plastic here. Then in front you have the high-density markers, and on top you also have a 3D camera to check the position of the patient. And we use that during a clinical data acquisition trial. So this is what the room looks like. You have a CT scanner. The IRIS prototype will stand here on the side. Here you have your afterloader, and then instead of a phantom, you have to imagine that this is where the patient is laying. And at this point, we acquired data from around 40 patients. Then one more thing is that we also try to look into how we can present the source tracking data well to the patient, or to the clinic, so that it can help them to make some decisions. And we did that by converting the data to dose metrics that are a bit more easy to understand, we think, for the clinicians. And also we show the uncertainty of our measurement system, so it's easier to compare if a specific deviation could have been just a measurement uncertainty, or if it was actually something that went wrong. Also, using this approach, we could already during the treatment make a prediction of what the final dose is going to be. And we think that can help if in the future we want to already have a signal in real time if we think the treatment is not going as planned. So then we get to the main outcomes. So a novel dose calculation algorithm showed good results for liver cases, and we think that brachytherapy could be a good treatment option for liver tumors because of that. A treatment verification approach called IRIS was developed from concept to clinical prototype. The treatment verification could make brachy safer and more efficient. And lastly, we also developed a method to convert source tracking data to dose metrics, and we expect that this can be used to detect errors in real time and predict the outcome from the treatment while it is still going on. And with that, I want to thank you for your attention and give the word back to the prorector.
Thank you very much, dear promovendus, for a very interesting presentation. We will now start with the opposition, and the opposition will be opened by the chairman of your assessment committee, that's Professor De Ruijser, and his expertise is radiotherapy, especially respiratory oncology in the University of Maastricht. The floor is yours.
Thank you very much. First of all, I want to congratulate you and your whole promotion team and your family for this excellent work. But I'm here to ask some questions, and I want to start to ask one of your paronyms to stand up and read proposition number 4.
Realistic 3D printed phantoms based on human anatomy can aid the development of novel in vivo dosimetry methods for brachytherapy without the need for additional human test subjects. However, to fully develop the approach for clinical practice, patient data is still necessary.
Thank you. Of course, I fully agree with that statement, but I want to make a transition to chapter number 6, where you actually do have some problems with motion in your phantom as well, and that's about pelvic tumors. And it will not surprise you if I ask you, how would you go for, in your idea, to start with the phantom to a moving target like in lung cancer, where you have different types of movements? What's your vision about that?
Okay, highly esteemed opponent, thank you for your compliment and your interesting question. So indeed, we saw that already using the phantoms that we had, that we had to change our approach that worked in the water phantom. But at some point, we transferred to real patients, but there was some difference in the motion, I think, between the actual patient motion and the motion that we simulated. So the motion platform is quite simplistic. We can only move the entire phantom, but of course, for the real pelvic area, there is all kinds of internal motion that can happen there. So that's, of course, is challenging, and also, one of the limiting factors of the phantoms that we have now. However, some of my colleagues are actually already looking into more advanced phantoms, so this is a field that is developing. There is already a thorax phantom with moving lungs. I think they are not fully realistic movements, but still there is some motion that you can simulate there. And we already have ideas to also do this for the pelvic area, to have a bladder that can inflate. So we are slowly doing that, but of course that research also takes some time. So I think the only real way to do that at this point is to analyze patient data, because that movement is too complex for...
And if you go to the lung cancer movement, I'm just talking about the nodule itself, so the primary tumor. Make it not too complex in the first place, looking at the lymph nodes, but just to the primary tumor. You have respiratory movement, but they've also movement because of the heartbeat. Yes. It depends on the location of the tumor, of course, and these are not in the same phase. Do you have an idea how to tackle this in phantoms?
In phantoms, so the breathing motion right now, it's simulated using motors that can push, but that's also only in one direction, while I think for most people when they breathe, their entire chest will expand, right? So I think yeah, maybe printing phantoms with more flexible materials entirely would be an option. However, I also think the more flexible you make it, the more difficult it will be to get to be able to replicate the motion that you try to add there. So I think there are ways to do it, but it is very difficult. Yeah, also for the heart, you could maybe have something that very quickly pushes inside as well, but yeah, it's for sure very challenging to create a phantom like that.
And if your promoter would give you, say, something, a sum of maybe 5 or 10 million euros or so, which experiment, I'm sure you can, but which experiment would you design then? If you, I mean, suppose that you have really good funding. Mm-hmm. How would you go? Because you're young, presumably ambitious as well. How would you go for, what would you do to make a phantom which is realistic and where maybe in 5 or 6 years we can indeed achieve the goal that nearly everything can be tested without the need to have some patients involved?
Yeah, there are a lot of ways you can go. So I know there are some groups that look more into having more like a full, like more like some kind of water tank where different organs can be printed and then can move more freely from each other. Yeah, but it's so difficult to speculate about this because I think 3D printing is one of these new fields that is developing so fast. So right now with the techniques that are here, I'm not sure if there is like a way to do it extremely accurately, but who knows, in maybe 1 or 2 years there is some new kind of 3D printing again that would allow us to do it. So it's a bit, I'm not that expert in
and
that.
And a short last question and also a short answer. How accurate should you be in your phantoms in order to replace the clinical input, because clinical input has also some uncertainty. So how accurate should you be, you think?
That's a good question. So I think if you know that you can be very accurate, it can be helpful because you can simulate some very intricate patient movements, and then you can check which ones you can see on your panel, for example. So I think, of course, very high resolution is always better. But if you just want to test if the general method works, it doesn't have to be millimeter accuracy, I would think is good enough.
Thank you very much for your answer. I give the word back to the pro-rector.
Thank you, Professor De Ruijser, for your opposition. Then we come to the second opponent, who is also a member of the assessment committee. That's Dr. Johansen. His expertise is dosimetry in the Aarhus University of Clinical Medicine in the Danish Center for Particle Therapy. And that is in Denmark. And thank you, Dr. Johansen, for coming all the way from Denmark. The University of Maastricht is always glad to have guests from abroad. The floor is yours.
Thank you. Thank you for inviting me. And also thank you for this very nice thesis and very nice work. I really enjoyed reading it. And I'm also very pleased to see that your work on this system is now going into the clinic, which is where it really is highly needed. And I'm looking forward for futures on that.
Yeah.
I also have a few questions. I don't know if you can bring up the thesis, but I have questions on page 87. It's on these the position accuracy of the system. So you have some very nice, you have a nice figure where you have some plots. You show that you can see 1 millimeter deviation if there's 1 millimeter offset, and so on. So for no offset, you have a mean value of x, y, and z, which is 0. Do you have it?
Sorry, page 87?
87,
okay,
yes.
Yeah.
Table 4.2.
Yes.
So I see that you have like the x is very nicely 0, 1, 2, 2.9, 3.8, which shows that you can actually show this offset. But in the total one, you actually get a 1.7 for the no offset. Can you explain why it goes so high?
Yeah, so so with this specific chapter, we used the head phantom, and at that point we were not very familiar yet with the full marker tracking approach. So do you want to know, so first of all, the 1.7 is that high because the z dimension for this, especially for this chapter, was quite bad. That was because the holder that we used here, it had 5 markers that were quite close to each other. And also at this point in time, we were thinking of using the acquisitions as well to detect some anatomical information. So we had the idea to have these markers a little bit on the side of the active area, but that meant that with setting up, I couldn't really put the head phantom like straight above the panel, but it had to be a little bit angled. And then by getting those projections, the uncertainty became much higher if you try to triangulate where all the lines are like more angulated. So at that point in time, we, that holder we later replaced by different holders with more markers, and we also tried to change the entire geometry of the setup to make it better. But that's why for this work the deviations were a bit higher than for the other chapters. Yep.
Yeah, sounds reasonable. So now you say you improved it, because here you have like an uncertainty of around 1.5 or something, I would say.
Yeah.
Do you know how much it is? How good is it now?
So we have different panels now because we have the clinical prototype. For that one, it is not, I think there is a table in the discussion that has all the exact numbers on page 163. So for example, in chapter 5, we did another test with the same panel, and there we had an improved holder, and there we could reach an accuracy of 0.7 with a standard deviation of 0.5, so that was already a lot better. And yeah, it sometimes we see it really depends on the geometry, and that's also why in our clinical prototype we chose to use this entire band so that we are not entirely sure where the clinic is going to place the panel compared to the patient, and that way we have a bigger field of view, basically, where we can accurately try to find the source position.
Very good. So let's assume now that you have in that ballpark like 0.7 millimeter certainty or something. If you now put it into the clinic and the clinician see like an offset of 1.2, 1.3, maybe 2, do you think they should trust it enough to like say that's a... Yes. Or how would you envision it used in the clinic?
Yeah, so that's also one of the questions that we have. And so in general, this uncertainty, we see that if you look at the average, if you have a lot of dwell positions, it will be a bit random, right? So the one time it will be 0.5 millimeter to the right, the other time 0.5 millimeter to the left. So then if you have enough dwell positions, I think in the end you can kind of still see that it is approximately in the right position. But if you see like an error that is in all of them, so all of them are moved to the right, then so that's challenging, and that's also why we looked into chapter 5 into the how to present this to the clinic. So how do we calculate? We try to convert it to those data and then combine it with those uncertainty bands, so it might give a more clear idea of if a treatment error happens or if it's just uncertainty of the system.
Yeah, and maybe just elaborate a little bit more on that, because it's hard to do something in real time in a paper because it's only been still photos. So I'm not sure, do you, like for instance, these dose accumulated or dose volume percentages figures, how do you present them to the clinic in this, or do you envision how to present those? Is it like this? You have this predicted one with an uncertainty bar. Is that changing throughout the treatment, or is that static? Or
yeah, so in real time will be very difficult, I think. However, what our idea is that you kind of have this dead time when the source, when you have finished treated one catheter, the source goes back to the afterloader. Our idea was to have some kind of pause there, and then you can show these plots with, like, at this point, if you continue, there was a small deviation, but if you continue, you will still reach this amount of dose. So then you also give the clinic some time to think, and then if they like it, they can still press continue. If they don't like it, they might say, okay, let's break it off, or maybe increase the dwell time somewhere else to compensate for that. But that's all just speculation and like thinking about how we can actually use this in the future.
No, for sure, and I think it's only gonna be possible to find out that when you have it in the clinic and talk to the clinician. So, yeah. And that's it's a really big challenge how to present this. So I think I don't have so much more now, but I would like to thank you for these answers.
Okay, thank you very much. Then we come to the following opponent, and that is also a member of the assessment committee. That's Dr. Tätgren. Her expertise is medical radiation, physics, and nuclear medicine in the Karolinska University in Sweden, and it is in Stockholm. And thank you, Dr. Tätgren, for coming all the way from Sweden, albeit online.
Okay, so first of all, I want to thank you for inviting me to read this interesting thesis. And I'm impressed really by the progress on the IRIS system all the way to the clinic with steps taken throughout all the chapters. So maybe I can start actually with something on the last chapter, which is not yet published. How is it progressing, your clinical inclusion, and what are your future plan for this?
Esteemed opponent, thank you for your compliment and your question. Yeah, so at this point we have around 40 patients. The idea was to include as many patients as possible because it is kind of like a passive data acquisition. I don't know if you can really call it a clinical trial. So in general, the patients only have to agree that there is some extra data that is being stored of them. And so around 40 patients. We only do the patients that are treated on the CT couch now because we made our device for that. But I know the clinic has plans to, in the near future, also start treating prostate cases on that same bed. So if that happens, that would be really nice for us because then we can also gather data from prostate treatments. And that would help us because right now we're just limited by the amount of patients the clinic has.
Okay, I see, but I'm looking forward to your final assessment of this. So you considering your chapter 4 then, when you use a head and neck phantom, first I can ask you, do you treat head and neck patients in Maastricht?
It's a good question. So I think there are a few patients sometimes, but in general there are not many at all in Maastricht clinic. So mostly it's endometrium, cervix or prostate that we treat with brachytherapy. I think there are maybe a handful of cases every year in different places. But the reason why we did that is also more practical because we wanted to print a head phantom, and it's a bit smaller, so it's faster and easier to print. So we want our system to be useful for any type of brachytherapy, of course. So it was also a nice way just to look into different treatment sites. Yes.
Yeah, I think so. And for the ones doing head and neck, we do it in Stockholm, but it's not so many patients, but we do sometimes like 10, 15 a year. And I was think that is like a treatment where the patient is sitting in a chair usually, and the implant is done before. So it would, and there really big, it's quite many fractions, could happen things. So I'm thinking, if you would use your system with this external marker panel, would you need to do something to the fixation of the patient sitting like in a chair, or change that to have the set? Because then you could like perhaps move your head.
Yeah, yes. Thank you. I understand your question, I think. I'm not fully familiar with the entire treatment procedure for these cases, but of course for us, if we know the exact position of the head, it would be very useful, because then we can more accurately reconstruct the source positions. The only thing is that with our trial and with our system at this point, we try to not ask the clinic to have to change too many things, because it's more like still an experimental device. And if such a fixation makes it much more uncomfortable for the patient, I don't know if it's the right way to go. But yeah, from a physics point of view, it would be nice if we know exactly where the head of the patient is, of course, yes.
I think one could use maybe those kind of vacuum cushions to like fixate the head, maybe. But thank you. Then I read also in your paper, because you use the imaging panel to determine dwell times and dwell positions. And then you wrote like not for dosimetry. And then you refer to Smith et al., one of the first publications where they tried using it for dosimetry, and it seems to have been abandoned since. Do you think it will be used for dosimetry in future, or do you see a point with doing that? Or
if I understand your question correctly, you mean Smith et al., the group in Australia. They also use an imaging panel. However, in their first work, they really tried to calibrate the panel. So looking at the intensities, try to verify the dose. So that's also something that we looked into with the water tank, and there we saw that it worked quite well. However, as soon as you move to a phantom that has an uneven shape and maybe even different materials inside, this calibration becomes, it still works somewhat, but the uncertainty becomes really high. So if I remember correctly, in Australia, in the distance direction, so perpendicular to the panel, they have an uncertainty of about 4 or 5 millimeter. So that would be too high to accurately reconstruct the dose and track the source. So you can still do it quite accurately in the plane of the panel, but not really well in the perpendicular to the panel, which is why we switched to the triangulation approach with the markers that we use now.
I see. So maybe I have time for a final question during this first round then. And I would like to go to the chapter 2, the dose calculations. And there I have like a more detailed question. First, I would like to say that this is, do you have, I can ask you first, do you have the cohort still available? Would you be able to recalculate and use it?
Yeah, so all the patients were treated in Munich because that's where they actually do these liver cases. They also shared the data with us for the simulations. So yeah, we can, I think, recalculate some things, but if you would like to do a study about that, maybe it's better to contact people in Munich for that, yes.
Yeah, I see. Because I had some comments on table 2 there, where materials were assigned from contoured structures, but not only material, also the density, the mass density, seems to have been assigned from contouring.
What was the question about?
Why didn't you use the CT density and just material assignment based on contouring?
So the issue with these CTs was that for the treatment they use contrast. So the liver has quite a lot of high density contrast in it, in the CT. So that's why we chose to use the contour of the liver and overwrite all the voxels with a specific density that we could use for liver. Because if we would use the actual values, we would get a lot of unrealistic artifacts, because that contrast changes quite fast between the imaging and the treatment itself. So the situation that it was when the imaging is not the same situation as during the actual treatment. So we thought it would be more fair to assign a standard value for that.
But is the contrast affecting also like bone and lung? But those are further away, so I understand the approach you took. Because if one looks at the table, it's like very different HU range there, and then just a single density. But I think this is a very minor comment, and maybe we should proceed.
Okay, thank you.
So, thank you for your opposition, Dr. Tedgren. And now we come to the following opponent, that's Professor Coy. She's a professor in medical physics, especially vascular imaging in the University of Maastricht. Professor Coy.
Thank you, Mr. Pro-Rector. Dear candidate, I would also like to congratulate you with your excellent thesis. And my congratulations also extend to the promotion team. Of course, I'm not here only to give compliments, but also to ask you questions. And you indicate in chapter 6, for example, that your image quality of the iris system is actually deteriorated by scattered photons. And in the diagnostic medical imaging, for example, using photon counting CT, nowadays we can also use energy discrimination of the photons. And I was just wondering, do you think also energy discrimination of the photons would be a potential opportunity to improve image quality also for the iris application?
Highly esteemed opponent, thank you for your compliment and also for the question. I think of course, if we could discriminate better between primary and secondary photons, it would really help us. However, it's probably also will make the entire device much more expensive, so I think that would be a limitation. We try to circumvent this already using simulation studies. So we had an idea to, because we do a lot of Monte Carlo simulations, and there you can, of course, score at the panel level which photons are primary and which are secondary. And then we try to, maybe using AI, try to filter out secondary particles, secondary photons actually in real acquisitions. So we were thinking about that, but yeah, if we have a very advanced panel where we can easily do that, I think that would be nice. But yeah, sadly, I think it would be a bit too expensive.
Okay, so for the point of view of the price, you would prefer to use AI. So if to kind of improve image quality, or?
Yeah, so, well, it was we have only been in a simulation study for that, so when we were trying that, we only had the phantom acquisitions, and we saw that for the phantoms, it didn't really work well, so we were not sure if it was because phantoms were not realistic enough. Now that we are gathering patient data, it might be worthwhile to look into that, but I think if that would work, that would already be a solution. If it doesn't work and photon counting detectors become cheaper in the future, then maybe that would be a better alternative.
Okay. Yeah, and if you would use AI, do you have any thoughts how you could kind of train the AI algorithm?
Yeah, so we, like I said, we would have to rely on very realistic Monte Carlo simulations. And then we can, from all the photons that would hit our detector, we can see which ones are primary, coming from the source, and which ones are secondary, so that's scattered somewhere. Then we can try to have our ground truth data, which are images of just the primary photons, and then the training data would be the full image with all the photons, and then try to go from those images with all the photons to images with only primary photons.
Okay, well, that's an interesting opportunity, I think, for the future. And I also noticed that you suffered from respiratory motion in chapter 6. So I was wondering whether you also have some thoughts how you could reduce the effect of respiratory motion in future applications?
Yes. So actually, we think that is respiratory motion because we didn't confirm it yet, but because we see these very repetitive peaks, we assume that it's that type of motion. The thing is that it doesn't necessarily mean that it is bad for the patient that there is respiratory motion, because the entire area is moving together. So there is a needle in there, and the source is going to be in there. And the idea is that the organs move together with the needle. However, for our tracking, it is a bit annoying, because then we see movement, but it doesn't necessarily mean that it's bad, right? So I don't know if we should somehow mitigate the effect in our data. But yeah, so one of the ideas that we have, so for example, the system that Dr. Johansen is working on, where they actually use an optical fiber that is also inside the patient. If you can also gather data inside the patient that is moving together with everything, you could try to combine all those results, and that would give you the full picture, I think. So yeah, it's at this point it's still a bit challenging, because to be honest, we didn't expect to see that much motion from breathing, because we thought we were quite far away from the lungs, but evidently there is still something going on. So yeah.
Yeah. Okay. And what about cading or breath holds or these kind of?
Yeah, so those are things that are being used for external beam radiotherapy. However, like I said, because the source should be moving with all the organs, for the treatment itself, it's not really necessary. So if we would then ask for gating, we are just making it a bit more uncomfortable for the patient, only so that we can track the source a little bit better. So I think that's probably not the right way to go. However, we could, for example, use those cameras to, if we can do it very accurately, see the chest moving and somehow try to couple that to the data that we have. So if we see that there is some movement, and we also see that the chest is moving, we know that it would be breathing, and if the chest didn't move at that point in time, we know that it was the source that was moving. Maybe something like that could be useful. Yeah.
Okay, thank you. I was just wondering for the iris system, as maybe a final question. You use only one imaging panel. And I was just wondering would you consider also using an additional panel? And
Yeah, so
would that improve the accuracy of the source detection?
I think so, because we see throughout all our measurements that there is one, so in perpendicular to the panel, the resolution of the uncertainty is always quite good. But the bottleneck is the distance, like that dimension is always a bit worse. So if we can have two panels, for example, that are 90 degrees, like one above the patient or below, yeah, below is difficult because of the couch. That could, of course, already decrease the uncertainties if you can align them well. And yeah, of course, there's also like, yeah, that might be very far in the future, like trying to use, for example, an actual CT scanner itself is difficult, but you have like a detector that can rotate around the patient. If you could work together with vendors that develop these devices and somehow combine these things, that would be really nice. And yeah, then you could get a lot of angles, right? So yeah, but that's very far in the future, I think.
Yeah, that's okay. Yeah, I'm satisfied with your answers, and I give the word back to the prorector.
Thank you very much, Professor Kooi, for your opposition. Then we come to the following opponent, that's Dr. Roelofs. He is a medical physicist at the Maastricht Clinic at the University of Maastricht. And today he has also accepted the role of secretary of this committee, for which I'm very grateful. The floor is yours.
Thank you, Mr. Prorector, and thank you for the invitation to be part of the opposition today. Congratulations to your work, dear opponent, and congratulations to the promoter and co-promoter of this work. And I'm glad to receive this work. I'm happy to be fed with knowledge, as I say, for the field of brachytherapy, in which I'm also a medical physicist. So, with that said, I'd like to ask one thing about the chapter 6 as well. The clinical implementation, you can imagine that that is significant for our work. And I'm glad that you managed to use the system for the first measurements with clinical patients. And that is of great importance. The next step, of course, is to really use this in a clinical setting, which I'm really looking forward to. I'd like to ask you, what do we still need to do in that sense? And how much do we need to do? And what are the hurdles to implement such a system in a clinical way?
Esteemed opponent, thank you for your kind words and your question. Do you mean like what technical things we still have to change on the prototype, or more what does have to change in the clinical workflow to
I think we've got about 8 minutes. The floor is yours.
Okay. So all right. So on the technical side, there are still some challenges. So as you saw in chapter 6, there were some, like the quality is not really always high enough to really find the markers. So we need to have some software improvements there, I think, first to try, to really find all the source positions accurately and be able to triangulate the source. There are several ways to do that, which I think I also describe in the thesis. But for maybe the clinical implementation is also interesting. And now I lost my thought. It can be, if we want to implement it, of course, it's important that it's clear for everyone what we can detect, and also that we don't give too much extra work to the clinic, I think, because if we do that and make it very difficult to set up, I think then we will create a lot of false positives, because then there will be something wrong with the setup, and so that's something we probably should really look into. I had something in my mind, but I can't get it back now. So, yeah, I don't know.
That's no problem. When you've got all the way to go, some thoughts might wander, and you might lose them along the way.
Yeah.
No problem. One of the problems that I'm facing daily in my clinical work is the challenge of getting research and development into clinical use. Although the path from a good idea until the prototype is long, there's always the transition from a good prototype, like yourselves, towards clinical use. Sometimes we're not even allowed to do so. So I'm talking about legislation, which is hampering innovation in that sense. So that's the medical device regulation, more specifically. Do you see any way to improve the transition from research into clinical use with respect to legislation and what we need to do for that?
Yes. So, I mean, of course, it might hamper the research a little bit, but I also think it's very important because, yeah, we're still a hospital, so the safety of the patient should always go first, of course. But I think already in this thesis we show that using those 3D printed phantoms, we already could skip some steps, because in a previous scenario without those phantoms, we would have gone from the water tank maybe immediately to a patient, and then there is a very big gap you have to bridge. So I think that already helps. And yeah, I think the way we did it now is actually, so sometimes maybe I call it a clinical trial, but it's more like a clinical data acquisition study. So you do measurements, but you don't give the outcomes of your measurements directly to the clinic or the patient. So even if you think something goes wrong, you don't tell the clinic yet, because it's still a prototype device that has not been fully verified yet. So I think these types of trials, maybe they are very specific for new devices, but I saw that within Mastro there was not really a framework for that yet, so we kind of had to follow all the rules that normally are followed for an actual clinical trial, which gave us some extra work, which was maybe a bit unnecessary in the end, which is also understandable because Mastro is not a huge, like the MUMC, a much bigger clinic. But maybe if we want to implement more of these technological devices in the future, we could somehow think of a way to, if we're only going to acquire data, then maybe there don't have to be very strict rules for that.
And those rules would refer to the patient, or the rules towards personnel?
Yeah, so, for example, the patient, of course, needs some information on what is going to happen. But if we saw, especially at the start of the trial, that a lot of the patients, they didn't want to join. And it was basically because they got like a lot of pages where we explained the entire thing like a normal clinical trial. And in the end, it was only for them to agree that we're going to save some additional data. And I think that scared a lot of patients and also made it seem way bigger than it actually was. So I think, of course, there needs to be a balance, because it's important that patients are informed very well of data acquisition studies they might be suddenly included in. But I also, this could also be maybe a hurdle for them. Yeah.
Okay. Related to fear, there was one of your propositions referring to that. May I invite one of your paronyms to read out loud proposition number 7?
Nothing in life is to be feared, it is only to be understood. Now is the time to understand more so that we may fear less.
Thank you. So the fear for the unknown, for a patient, the unknown fact that you don't know what's going to happen with your information, that I can imagine. Are there other points which we should fear less, you think?
Yeah, so the main reason why I added this proposition was because I feel at this point we don't measure a lot of treatment. Yeah, there is not many treatment verification performed, only in a handful of clinics, of course. And therefore, there is not a lot of data. So then you can also feel like, okay, the treatment outcomes are pretty good, so we can just keep it like this and just assume that we're doing everything right. But if you implement these kind of things, you might see that, for example, we make a lot of mistakes, which is, of course, not nice to hear, but I think in the end, it will be beneficial because, of course, it will be better for the patient if they know immediately after the treatment if some type of error happened.
Yes, I can imagine. Thank you.
Thank you, Dr. Roelofs, for your opposition. Dear candidate, Mr. van Wagenberg, the time appointed for the defense of your thesis has passed, and this committee will now withdraw to discuss the quality of your manuscript and the way you defended it. And I request that you and your company online and on site await the results of our deliberations and our return in this room. And having said that, I suspend the meeting.
The PhD defense has now ended. The degree committee will debate the candidate's performance behind closed doors. This process usually takes about 10 minutes.
Long road to the south side, 7 miles in my rearview mirror. I know what it felt like. My goal's only getting clearer. East side to the west side. No place like home. If it's questions that you've got, go the extra mile and die. I know what's on the line. I know you know that I can't read your mind. Years can't fly by now, don't waste all your time. Cause I'll go the extra mile. Long road to the south side, 7 miles in my rearview mirror. I know what it felt like. My goal's only getting clearer. East side to the west side. No place like home. If it's questions that you've got, go the extra mile and die. On the dash, got my laces tied. Long road, I don't waste no time. Break rules because fate decides. With the team and we chase the light. I make a move, fall down, shake it off. I hate to lose, bad branch, break it off. No room for negativity, praise and love. Prepare for deep part cause we're taking off. Hit the mileage, traveling so far from home. Gathering knowledge, other connections. I put the time in to get everything I ever hoped for. It's a challenge and we all in. It's a better future that we go for. Even though these nights seem long, I know that I am never on my own. Know you've won the battle once you've grown. South side, 7 miles in my rearview mirror. I know what it felt like. My goal's only getting clearer. East side to the west side. No place like home. If it's questions that you've got, go the extra mile and die. Long road to the south side, 10 miles in my rearview mirror. I know what it felt like. My goal's only getting clearer. east side to the west side. No place like home. If it's questions that you've got, go the extra mile or not. What's on the line? I know you know that I can't read your mind. Years can't fly by now, don't waste all your time. 'Cause I'll go the extra mile.
the online because of the.
Oh, the online.
Yeah, it's because the boxes are very.
U kunt op tafel.
I reopen this academic ceremony. Mr. van Wagenberg, the degree committee here present has assessed the quality of your manuscript and the way you defended it. And in view of its positive verdict and taken into account your previous qualifications, the degree committee has decided to grant you the degree of doctor. And Professor Verhagen is authorized to confer upon you this academic distinction in accordance with Dutch university custom. I invite him to now take the floor.
But first I have a small question for you. Do you promise to work in accordance with the principles of scientific integrity at all times, to be careful and honest, transparent, independent and responsible?
Yes, I promise.
By the authority vested in us by law and in conformity with the decision of the committee here present, I hereby confer upon you, Teun Pieter van Wagenberg, the degree of doctor, and grant you all the rights attached to this by custom and law. As evidence of this, I now present you with the degree certificate signed by the rector, the secretary, and the other members of the committee, and affixed with the official seal of the university. Dr. Teun, I have one more task. About the only thing I had to do actually today was write a little laudatio for you. I have 2 pages, as you see. So when I think of you, and especially your place in the physics research division in Maastricht, I think of you foremost as a strong, silent force. And by this I mean that you are a person who always thinks twice before speaking, which, and I already apologize in advance, but doesn't come very naturally to many Dutch people. Sorry. And a real force in 2 senses. To keep your research moving forward, you are very persistent. And the second point is that you are, besides that, also a force that plays an essential role, I think, in motivating the team, keep up the work and the complex research that we sometimes do. However, for me, one of the most baffling things about you, about your whole journey with us so far, is the way that your international colleagues managed to pronounce your name. Instead of Teun, I heard your name being mangled in about every possible way. Some call you Teun, I heard Teun, Toon, I heard everything. It's found a little bit strange. Sometimes they're talking about you to me, and I have to wonder, who are they talking about? Before I realize it's you. Anyway, I think it's now too late to correct them, but maybe tonight during the party you might have another try. So going a little back in history, you were with us since 2018, first doing a master thesis about the complex topic of using artificial intelligence to extract material characteristics from dual energy CT images for proton radiotherapy. Sounds really complex, and that's what it is. This was a combination of advanced image analysis and AI, and which was quite novel back then and still actually is today. It took a little bit longer than average to get your degree, and if I remember correctly, you graduated either just before or just after the start of the corona misery in March 2020. Right? So difficult times, and despite these difficult times, you persevered and started a PhD with us on a completely different but also complex topic, what you have shown today, of course, the development of a safety system to verify the radiation dose in brachytherapy for cancer patients. As we heard today, small errors in radiation dosage or misplacement of the source can have grave and even catastrophic consequences for the patient. So the IRIS system is really important. It grew out of a relatively simple idea, but still needed then about 5-7 years, more even, 8-9 years to develop. And this shows once again that the path from bringing an idea all the way into clinical prototype is very hard and requires many years, but it can be done. And it's actually quite exceptional that one single team can actually do this. Of course, I also asked around to your colleagues to provide some little snippets about your life and interaction outside Maastro. The one thing that comes back a lot is that they seem to doubt that you have a home. Apparently, you spend so much time at Maastro that some start to wonder. And the only thing that can motivate you to go home are apparently hunger and bonding with your cat. And I have to say that I also have the same two reasons. So I just think that that means that you really like your job. And in fact, you feel so well at home at Maastro that I've been told that when you work with your noise-canceling headphones on, you sometimes are singing very softly. And that seems to have a relaxing or even a bit hypnotic effect on your neighbors. So that's an extra. But besides working, you also like playing board games with the team, and you like it even better if you win, which you seem to do most of the time, I've been told. Especially games that involve strategy, you seem to beat everybody else. Games that involve deceit and lying, you're not so good at, but that's maybe a good thing, I think. I would expect that you would then also be good at planning, but I've been told that you leave that to others, that you show up at events, but preferably don't do the planning itself. So professionally, you had plenty of international recognition, which was not really mentioned today in your still young career, especially by winning 2 major awards at the annual ESTRO conference. And this is the biggest conference in our field in Europe every year. You won 2 prizes for your brachytherapy work, among them the prestigious ESTRO Lecta Prize for Best Brachytherapy Presentation. And this is quite curious, because Maastricht is known as a center of excellence for brachytherapy, together with the company Varian. So in principle, we have absolutely nothing to do with Electa. They're actually big competitors, and that's even more strange that they would give you an award, but okay. Maybe somebody made a mistake at Electa, maybe somebody got fired, but I think it's actually, again, just a recognition for your work, as it is independent from which company we are collaborating with. Winning such important awards has made your colleagues tell me that you should get an award for getting so many awards. Well, today we did that, right? We've given you one of the biggest awards you can ever have, a PhD in your life. There is not much bigger than that. So, one thing I noticed is that some clear trend over time is that the number of participants at the ESTRO meeting has been declining. Some say that's because of Corona, but I actually think it's because they know that you are going, so nobody else can win a prize, so they just don't show up. Okay, 2 more examples. You are a cool-headed person, I find, but you're actually also easy to excite. And that doesn't mean that those 2 are contradictions. Let me give an example. Gabriel told me that you were cool-headed enough to feed his spiders during vacation. I never heard about those spiders. I need to know more. And the other thing is, of course, that you talked about your PhD today, but you now started doing a postdoc, which is again on a complex and very novel topic, but completely outside what you did for your PhD. So it's easy to make you enthusiastic. You also try to carry that over to other people, for example, by your attempts to learn Chinese. And that's not only a difficult and different language, but also a different way of thinking, I think. That can always come in handy, of course, that if the Chinese keep expanding their circle of influence and they will come to us and ask, take us to your leader. You may be the only one who can actually reply to them. Oh, by the way, how do you pronounce Teun in Chinese? Do you know? No?
Just
Teun, as I mentioned, you're staying with us for 2 more years, so postdoc, at least 2 years, I hope. Scientifically, I look forward to attacking yet another challenging problem, but I also look forward to the way you will continue to keep the team together. That's also very important. I saw you leap at the opportunity to become the buddy of newly joined co-workers, eager to learn what they are doing, but also eager to make sure they fit in the team. Teun, enjoy very much this very special and unique day in your life, so we'll always be able to look back upon this as one of your best memories. This is an award that no one can ever take away from you, unlike maybe the Electa Award once they realize their mistake. So, yeah, I've said many congratulations.
Thank you very much, Professor Verhagen, for this very nice laudation. Dear Dr. van Wagenberg, also on behalf of the University of Maastricht, I would like to congratulate you with the degree you have acquired. And I extend my congratulations, of course, to your partners who have supported you all the way. And of course to your supervisors, Professor Verhagen and Dr. Fonseca. And of course your family, friends and colleagues on site and online. And I hope you can celebrate this day because it's probably the most important day in your scientific career, one of the most important days. So I hope you will have a great remembrance of that. I would like to thank the members of the opposition for all their hard work and of course the PEDEL and the technical support team who made this hybrid ceremony possible. Then I'm about to close this ceremony, but I have a few comments still. En ik ga dat even doen in het Nederlands voor het publiek, dat is misschien net zo makkelijk. Wij gaan zo dadelijk deze ceremonie sluiten. De pedel zal u dan vragen de zaal te verlaten en vast naar de refter te gaan, waar u alvast een drankje kunt nemen. Wij gaan hier dan nog een foto maken met professor Tedgren op de achtergrond. Dus de fotograaf moet zeker blijven graag. En daarna gaan wij nog naar de trap in de hal, waar we ook nog een foto maken van deze groep. En daar kan ook eventueel familie bij op de foto, zolang we maar een fotograaf hebben. En als u dan in de zaal allemaal denkt, maar wanneer kunnen wij dan eindelijk de dokter feliciteren? Nou, u wacht gewoon in de refter en dan is de volgorde heel simpel. Wij gaan eerst en dan komt u. En dat gezegd hebben, sluit ik deze ceremonie.
It looks a little crazy with a large.